In this video we're looking at the critical points method of sketching a graph, and so we're going to sketch this equation x plus 1 over x squared plus x minus 2, or if we factorise the denominator we get this format. Now let me say right up front, there's a number of slides and it may feel a whole lot more complex than it might need to be, but once you understand how the critical points method works, it shouldn't be too big a deal at all. Okay, we start the critical points method by just looking at the intersection points as we would normally do with graphs anyway. When x is 0, we substitute and get negative a half, and when y is 0, how do we make y 0? The numerator has to be negative, beg your pardon, 0. So there's our first 2 points, and as you go through the information, what we want to be doing is plotting these points and these regions consistently as we go. Okay, the next part of critical points is considering vertical asymptotes. So where does x not exist, or what are the domain restrictions on this graph? Okay, we want to change this into its products form so we can look at these things, and obviously there's an asymptote at x equals negative 2 and x equals negative 1. I can't have a 0 in either of these brackets, which is what a vertical asymptote defines. Again, once we've made that decision, we plot it on the graph. So I've got my points, I've got my asymptotes. Now the next stage we're going to look at is looking at considering what's happening in the different regions of the graph. And we're dividing the graph into regions by looking at the vertical asymptotes, looking where the root or roots of the equation sit on the graph, and using the values of the products. Now, values of the products are, this is one product, this is the other product or term, and this is the third one. So we have 3 things here, and we're going to look at each one of those graphically. Now, what we do then is, I'm going to look at this. This thing here is, in its own right, a linear equation. This is a linear equation, and this is a linear equation. So I can sketch these 3 pieces onto the graph and just observe where the combinations are positive and negative. Y equals x plus 2, y equals x plus 1, and y equals x minus 1. Okay, so remembering that the x plus 1 is our numerator, and these 2 things represent the 2 products in our denominator. Okay, so what I'm looking at is, for this line, well, it's negative when it's less than negative 2, and it's positive everywhere else. In other words, when I start looking at the regions of this graph, if I'm looking at the region between 2 and negative 1, this here, well, whatever values I have in here, this product is positive. Okay, so negative 1.9, when I add 2 to it, y becomes positive. So I've got a positive piece of the equation, but I have 2 negative pieces as well. And I'll show you in a next slide how to pull all those together. But what we're doing is we're creating regions. There's a region below x equals negative 2. There's a region between the asymptote and the point of intersection. There's a region then from this point to the next blockage, the asymptote. The x-axis, the y-axis doesn't matter. So there's another region here, and there's a 4th region beyond that asymptote. Okay, so this is what it looks like. My value of this piece is negative, is negative, is negative. Up here it's positives because it's above the x-axis. Okay, and all I've done is labelled the value of this particular component, this particular product, and I'm going to put that back into the equation in the next slide to see how it all works. So all you need to do is recognise that each of these 3 things are the pieces or the different products in the equation itself. Now, once we've got all those positive and negative bits together, I do also need to think about, is there a restriction in a horizontal plane? Okay, so we're looking at horizontal asymptotes. And what you would be expected to know is how to find that horizontal asymptote. So we're finding the limit as x approaches infinity. We always divide by the highest power, which is x squared in this case. So I've divided each term by x squared, and I have 1 over x squared, etc. Now, the reason we do this is because 1 over x, as x approaches infinity, equates to a value of 0. So 0 plus 0 is 0. So what I've got then is a horizontal asymptote at y equals 0 on the x-axis. So as I begin sketching this thing using my different regions from the previous slide, I also know that there's a horizontal asymptote working out on the x-axis. So let's put all this stuff together. Here's my horizontal asymptote, there are my vertical asymptotes, and here are the parts of the equation. Now, I'll explain this okay, let's look at it. I'm going to explain this on this graph here. Now, what I've got is, look at the equation. I have a negative value for x plus 2. So this piece will be negative below negative 2. This piece will be negative. Negative times negative is positive. X plus 1 is also negative. So the answer to this is negative. So what I know is that somewhere down here, well, actually not there, but so let me do that again. Somewhere down here will be the curve for that. Now, it can't go above the asymptote here, and it can't go past the asymptote here. So you'd have a pretty good bet that it is shaped like that. The next region is from 2 to negative 1. Now, x plus 2 is positive, so that thing there is positive. But x minus 1, the other part of the denominator, is negative. So I have positive times negative. That gives me a negative answer. I'm going to times it by a numerator, which is also negative, which means the answer to y lies in this region here. It's positive. Again, if it's positive and it's approaching an asymptote, it's most likely, and we know that this is the point of intersection, so it's most likely doing that. It's going up towards the asymptote. Now we use these regions again, so I'm looking between 0 and the asymptote here. So I've got a positive first part of the denominator, a negative part for the second part of the denominator. So I've got positive, negative, and positive. So positive, positive. The answer here is negative. So the answer between this and this lies in this region here. Again, if we're approaching an asymptote, it goes through this point, it goes to this point, it's headed towards an asymptote, it's most likely going to do this. And just quickly last, the three components are all positive, which means I have a positive answer for y, and you get the drift. We're up here now. Okay, now if I try and draw this, and let's choose a colour you can't miss. Okay, what I've got, and just bear with me and I'll make sure you can see this. Okay, so what I've got now is something that's going to look like that. Okay, so you see down here an asymptote along the x-axis, an asymptote. I've got a positive section here, which must be an asymptote. It must go through there, it must go through there, and must head down there. Now, I'd be a bit more careful about passing through that point if I'm drawing this as a sketch. And finally, we have an asymptote up there. And this is what the graph looks like in its final state. So in terms of critical points, what we've done is we found all the critical points and considered what's going on around them, and demonstrated that this section has to be negative. We've found the asymptotes, we found this asymptote, the points of intersection, and we're just interpreting the information of positives and negatives to give us the position of the graph, and with a bit of knowledge, understanding how asymptotes work, to understand that if it's a positive region, it must be approaching the asymptote from here and here. Okay, so although this has now been about 10 minutes, you know, if you did it from start to finish, it should be a whole lot quicker than that by just interpreting and building this thing up. Obviously, you need to end up with a graph like this. So the graph on my previous page would be working, and then you'd be wanting to finish with a well-produced graph. And there is critical points.